For Physics 232C, this will be an introduction to Chapter 15. That's the first chapter in the course, which is on electric charges, electric forces, and electric fields. So Chapter 15 has 5 sections, and electric charges, Coulomb's law for multiple charges, electric fields, and charged particles in electric fields. And the purpose of the video is to give an introduction to Chapter 15. It doesn't replace Chapter 15. You'll still have to read Chapter 15, but it'll start with an introduction. What is electric charge? Well, electric charge is a property of matter. All matter is atomic, and any atom contains a nucleus with a positive charge equal to Z times E, where Z is the atomic number, and E is a universal constant, surrounded by a cloud of electrons, Z electrons, where Z is the atomic number. Now this constant E is kind of the basic charge of the universe. It has the value 1.602 times 10 to the minus 19 coulombs. Proton charge is plus E. The electron charge is negative E. Now, that's an atom. What about an object which will be made of many atoms? Well, an object may be electrically neutral, like an atom. The atom has charge plus Ze in the nucleus and minus Ze from all the electrons, so the total charge is 0. That's called electrically neutral. And an object may be electrically neutral. Or it may be net positive if there are fewer electrons than protons. Or it may be net negative if there are more electrons than protons. We'll use the letter Q to stand for the charge of a macroscopic object. And Q is just the sum of all the charges of the subatomic particles. It's the number of protons times E minus the number of electrons times E. So if the number of protons and electrons are equal, the charge will be 0. But the charge could be positive or negative. All right, so that's electric charge. It's a property of subatomic particles. Now electric forces. Well, I guess everybody remembers from grade school, like charges repel and unlike charges attract. So suppose I have 2 positive charges. Let's make the positive charges red. Suppose I have 2 positive charges. In other words, 2 objects, think of them as small spheres, in some region of space. Each one will experience a force directed away from the other charge, the other object. So these are repulsive forces. The little spheres are repelled from each other. The forces are equal but opposite, consistent with Newton's third law. Now let's use blue for negative charges. So suppose I have a red charge, positive, and a blue charge, negative. Well, they will have equal but opposite charges of attraction. Each sphere is attracted toward the other sphere. Or that is to say, each sphere experiences a force directed toward the other sphere. Now, there might be other forces in the system, but this would be the case of two isolated charges. Two positive charges, the forces are directed away from each other. Or two negative charges. Like charges could either be two positive or two negative. If you have a positive and a negative, unlike charges, the force will be directed towards the other charge. Now, the charges here don't have to be equal. This sphere might have a larger positive charge than this sphere. So this sphere might have a charge of, 5 coulombs. And this sphere might have a charge of 1 coulomb. They will have equal but opposite forces directed away from the other charge. Now, the strength of the force, or really, this is an interaction, so for every interaction there are actually two forces. The strength of the force was first measured by Charles Augustin de Coulomb, who lived 1736 to 1806. He lived about the time of the American Revolution. So while the Americans were fighting the English in the American Revolution, Monsieur Coulomb was measuring the force between charged objects. Now, before we go on to the measurements, let's have a brief history of the science of electricity, because this phenomenon has a very long history. The first observation of electricity and the first description was by Thales of Miletus. This man Thales lived in the civilization of ancient Greece. He lived in the city of Miletus, which is actually in what is now called Turkey. He lived from 624 to 548 BC. So we're talking about many centuries ago, millennia ago. Thales is considered the first scientist of Western civilization. What Thales observed and wrote about is that when amber is rubbed with wool, it will then exert attractive forces on light objects like feathers or bits of straw. Amber is a kind of material, it's actually a fossil of plant resins. Today we call this effect static electricity. So Thales knew electricity as an attractive force, but a very weak force. So it could only be observed for its action on objects like feathers or little bits of straw. Now, moving ahead 2 centuries, William Gilbert was an English physician and scientist, and he observed that many materials, not just amber, can be electrified by rubbing with other materials, not just wool. And he named the effect electricity. That's where we get the word in the English language for electricity. The word was coined by William Gilbert. Where did he get the word? He named this phenomenon after the Greek word for amber. The Greek word for amber is electron, written in Greek letters, So he showed that static electricity, interactions, forces, can be obtained by electrifying objects, and not only by amber, but he named it after amber because it was first observed as a phenomenon of amber. Now, moving forward a little more, the first American scientist was Benjamin Franklin. He lived 1706 to 1790. Naturally, he lived at the time of the American Revolution. He was very much involved in the American Revolution. So he lived at the same time as Coulomb. And Franklin invented the theory of positive and negative charge. Because at the time of Franklin, other scientists had shown that the forces between electrified objects could be attractive, but they could also be repulsive. Thales knew about attractive forces. Gilbert knew about attractive forces. Later scientists discovered repulsive electric forces. And Franklin invented the theory that that's because there are two kinds of charge, positive and negative. And like charges produce repulsive forces, unlike charges produce attractive forces. Of course, Franklin is famous for the kite experiment that showed that lightning is an electrical phenomenon. All right, now let's go back to Charles Augustin de Coulomb, who measured the forces between charged objects. The force is not very strong. Well, actually, the electric force is very strong. It's way stronger than gravity. But it's hard to electrify an object so that it has a large charge. So the forces between small charges tend to be pretty small. So Coulomb had a hard job to measure this weak force. But he was a careful experimenter. He had a kind of torsion balance. And he determined that the force between charged objects, two charged objects, any force requires two objects. One object to exert the force and one object to experience the force. And any force is really one half of an interaction. For every action, there's an equal but opposite reaction. For every force, there's an equal but opposite force. So if I have a charge here with charge 1, I have a charge here with charge 10, they will experience repulsive forces which are equal. And the strength of the force is a universal constant K, which we call Coulomb's constant, multiplied by the first charge, Q1, multiplied by the second charge, Q2, and divided by R squared, the distance between the two charges. So the distance between the two charges, if these are little spheres, this would be the distance between their centers. That's R. So really I ought to show this extending to the centers of the two spheres. It's an inverse square law. That must have been a shock because before Coulomb, Isaac Newton had shown that the force of gravity between masses is also an inverse square law. So lo and behold, whoever created the universe seemed to like 1 over r squared forces. Now, of course, we have to have a unit of measurement for charge, and the standard unit of measurement for charge is called the Coulomb, named after Monsieur Coulomb, abbreviated by a capital C. And as for Coulomb's constant, which determines the strength of the force, and which is universal, that constant is the same for any two charged objects in the universe, just a universal constant. It has the value 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. We call that the Coulomb constant. You see, it's very large. It's approximately 9 billion in terms of engineering units like newtons, meters, and coulombs. It's so large that it's almost impossible to create a charge as large as 1 coulomb. Most charge objects will have a charge just a tiny fraction of a coulomb. Now, we're not quite finished with the history. So let's go ahead into modern physics, the physics of the late 19th, early 20th century. J.J. Thomson was an English scientist, physicist. He lived 1856 to 1940, so his life extended into the 20th century. J.J. Thomson discovered the electron. What he did was he discovered an elementary particle with charge -e and mass m, and all electrons, all of these charges, he called them corpuscles. Every corpuscle has exactly the same charge, -e, and exactly the same mass, call it m sub e. E is that universal charge, 1.602 times 10 to the minus 19 coulombs. You see, it's a tiny number. So to accumulate a lot of charge in a macroscopic object, you have to move a very large number of electrons. The mass of an electron is also very tiny. It's 9.11 times 10 to the minus 31 kilograms. So measured in kilograms, it's a tiny, tiny number. The electron is the subatomic particle that's responsible for the structure of atoms, molecules. All of chemistry is concerned with the behavior of electrons in atoms and molecules. Well, that's the basic negative charge in the universe. What's the positive charge? The positive charge is called a proton. There's also a similar particle called a neutron. The proton is positively charged. The neutron is electrically neutral. Now, it was Ernest Rutherford. This is wrong. He lived, he died in 1937. So that number that I wrote down is definitely wrong. That must be 1871. So this must be 1871 to 1937. It was Rutherford who discovered the existence of the atomic nucleus. At the center of every atom, there's a tiny but massive particle, which we call the nucleus. It's some combination of protons and neutrons, depending on the mass, the isotope, the atomic number. The charge of the nucleus is E times the number of protons. The neutrons have no charge, although they do have electric properties, but they don't have any electric charge. So an atom can be neutral because the electron charge has the same magnitude as the proton charge. So some integer number of electrons surrounding a nucleus will be electrically neutral. It's still, even today, a mystery why electrons and protons have exactly the same magnitude of charge. Just an experimental fact. So this is the starting point for the study of electric forces, the quantitative or mathematical description of electric forces, first observed 500 years before the birth of Jesus of Nazareth by Thales of Miletus, now known quantitatively. To be very specific, the electric force between spherical charged objects is given by Coulomb's law. This way is we have two positive charges with charges Q1 and Q2, and some distance between their centers R. Then the force on Q2, call that F2, is equal to K Q1 Q2 over R squared. Of course, force is a vector, so it has to have a direction. So the direction is R hat. The direction R hat is directed away from charge number 1. So R hat is a unit vector, a vector with length 1, directed away from Q1 at the position of Q2. So that's the force on Q2. K Q1 Q2 over R squared R hat, and K is a universal constant. And at the same time, there's a force on Q1, call that F1. And F1 is also K Q1 Q2 over R squared. It's consistent with Newton's third law. The forces have equal strength. Even if Q1 and Q2 are different, the two forces have equal strength because they're both proportional to Q1 multiplied by Q2. But it's in the opposite direction. So its direction vector would be negative R hat. R hat points, I've chosen R hat to point in the direction from Q1 to Q2. Well, then negative R hat points in the opposite direction. So there's minus R hat. And if Q1 and Q2 have the same sign, both positive or both negative, these forces will be both directed away from the other particle. But if Q1 and Q2 have opposite signs, then the signs of the force vectors will be opposite to the picture here, and the two charges will experience forces of attraction, forces directed toward the other object. Now these objects, these could really be small objects of any shape. I usually talk about them as particles, very small objects. They could be spheres. They'll have positions x1 and x2. Now remember, position in 3 dimensions is a 3-dimensional vector. So x1 would be x1, y1, z1. x2 would be x2, y2, z2. The relative vector, so let's draw another picture here. Let's put this in a different color. Let's suppose we have a charge q1 at this point, x1. That's the position of x1. I have some coordinate system out here. This might be the x-axis. This might be the y-axis. Someplace there's an origin. x1 is the vector from the origin to the particle q1. So let's see if I'm able to draw a little vector x1. That's the vector x1. Now someplace I have another vector, another charge. So someplace I have another charge. Let's put it also in green. So here's another charge. And it will have a position x2. Hope you're taking notes. Let's draw the vector x2. x2 is the vector that goes from the origin to the position of the second charge. Well, see if I can do this a little better. So x2 goes from the origin. Here's my coordinate system. Here's x1. x1 is the vector from the origin to q1. So there's x1. x2 is the vector to the second charge. So there's x2. Maybe I can clean this up a little bit. This is x1. This is x2. R is the relative position vector. R is x2 minus x1. Now you remember how you add vectors. R is this vector. Let me put R in another color. Here's the vector R. That's the vector R. That's the vector R. It's x2 minus x1. Or I could say x1 plus R is x2. So if I go in the distance x1 plus R, I end up in the displacement x2. So R is x2 minus x1. Or in terms of coordinates, x2 minus x1, y2 minus y1, z2 minus z1. It's the vector that goes from q1, so this is q1, to q2. So this is q2. R points from q1 to q2. R, the vector, I indicate it's a vector by putting an arrow over the symbol, is R, the magnitude of the vector. That's just the length of the vector. So R is a vector. R is not a vector because it doesn't have an arrow over it. What is it? It's the magnitude of the vector R. In other words, it's the distance from q1 to q2. I really should say it's the distance from the center of q1 to the center of q2. So if I really wanted to be accurate about it, I don't think I'll bother, but anyway, I would indicate the vector from the center of q1 to the center of q2. What's r hat? Anything which is a vector has to have an arrow over it, unless it's a unit vector. If it's a unit vector, it has a hat over it, a caret symbol. R has magnitude R and direction R hat. So R is R hat. R hat is R divided by R. Divide both sides of the equation by the length. The force goes like R hat over R squared. R hat over R squared. We could write that as R vector divided by R cubed. This is an inverse square law because it's proportional to 1 over R squared. This is a unit vector. I could write it as R over R cubed. That doesn't make it an inverse cube law because there would be a power of r in the numerator. It's an inverse square law. And if these are the coordinates, x, y, x1, y1, z1, x2, y2, z2, r, the magnitude, is the square root of x minus x1 squared plus y minus y1 squared plus z minus z1 squared by the Pythagorean theorem. All right, so now we have the mathematics to describe the electric force between charged objects. Now let's work out an example. I think there's only one example. Given two charged particles, an isolated system. So in other words, these are the only two objects that are interacting. Call that an isolated system. Calculate the forces. Now, we have to know the value of the mass of the charges. So let's say Q1 is 1.2 coulombs, Q2 is 3.4 coulombs. And we have to know the positions. Well, let's say X1 is at the origin of the coordinate system. I could set up my coordinate system. So the coordinates of Q1, so this one's Q1, are 0, 0, 0. And let's say the coordinates of Q2, this one's Q2, let's say the coordinates of Q2 are 3, 2, 0. So Q1 and Q2 are both in the xy plane. They both have z equals 0. Q1 is at the origin. Q2 is at 3, 2. The x distance from the origin is 3. The y distance from the origin is 2. Now what's the question? Well, calculate the forces. There are two forces. So the answer will have two answers. There'll be two answers. There'll be, first of all, F1. That'll be half of the answer. And then there's F2. That's the other half of the answer. Because by Newton's third law, for every action, there's an equal but opposite reaction. So every interaction has two forces. Well, the problem says calculate both of them. Let's just calculate the force on Q2. So let's calculate F2. And step one, let's calculate the magnitude of the force. Remember, force is a vector. Every vector has to have an arrow. If I write F, that's not a vector because it doesn't have an arrow over it. If you write F and you mean it to be a vector, you don't know what you're doing. You have to write F with an arrow over it to indicate that it's a vector. If I write F, that usually means the magnitude of the vector F. You've studied vectors before back in Physics 231, so this should be familiar to you. Well, let's calculate F. It's K Q1 Q2 over R squared. K is a universal constant. It always has the same value. 8.99 times 10 to the 9th if I use standard units. Q1 was 1.2. Again, using standard units. Q2 is 3.4. And I divide by R squared. R is the distance between the two particles. So let's put in a different color here. This is R. This is R. Between the centers of the two spheres. What's R? Well, R is the square root of 13 meters. You know, if I look at this little right triangle here, this is a right triangle. The sides of the triangle are 2 and 3. The hypotenuse is the square root of 2 squared plus 3 squared. That's the square root of 13. So I have to divide by r squared, that's 13. And I'm using standard units, so the units will all combine so that force comes out as newtons. And if you multiply these numbers together, maybe you want to use a calculator, it'll come out to be 2.82 times 10 to the 9 newtons. We're not done yet, because force is a vector. This gives me the magnitude of the vector, but what's about the direction? F2, I can write it as F2x, F2y, F2z. Well, there is no z direction. You know, the force F2 will be in the xy plane. So F2z is 0, so let me just write F2x and F2y. Projecting onto the x-axis, I'll have the cosine of theta, or this is the angle theta. That's theta. So if I project down this right triangle, the adjacent side is the x-coordinate. That's cosine theta. And the opposite side is the y component. So cosine theta is 3 over the square root of 13. Sine theta is 2 over the square root of 13 by trigonometry. So if this were a ln kappa problem, the answer you would have to submit would be F2x and F2y. There would have to be two boxes where you can write down a number. It'll be a number with a unit. The unit will be newtons. The number will be 2.82 times 3 over the square root of 13, or 2 over the square root of 13. That's half of the problem, because the problem says calculate the forces. Well, that's one of the forces. What about the other force, F1? You really don't have to do the calculation over again for F1, because you know F1 is negative F2. That's Newton's third law. Oh, actually, I do have a second example. So here's a second example. This is an example where there's superposition. Forces with more than 2 particles. So suppose we have a system with 3 particles. Capital Q at this point, capital Q at this point, and little q at this point. So this charge is coordinates 3, 0. This charge is coordinates 0, 3 in meters. This charge has coordinates 3, 3. And the problem is to calculate the force on the lowercase q charge. Now, because there are multiple charges, I have to use the superposition principle for this problem. And you'll read about this in the chapter 15. There's a section on multiple charges. And it's really quite simple. We calculate the force between any pair, and then we add those forces. But we have to add them as vectors. So let's call this charge 1. let's call this charge 2. We could call this charge 3, but it's just different from the other two charges because it has a different value of charge. So let's just call these 1 and 2. The force on Q due to charge number 1, we'll call that F1. So just think of these two charges alone. There'll be a force on Q in this direction. And we'll call that F1. That's the force on charge 3 exerted by charge 1. So that's F1. And similarly, we have a force F2. Which is the force on little q exerted by this charge. Now actually, if these two charges are equal, as indicated in the picture, these two forces have to be equal. So I should draw this a little better. There's F2, there's F1. And again, these are directed, or those are the forces on the center of the particle. It's really just the force on the sphere, I should say. I really should indicate that these are vectors. To indicate a vector, you have to put an arrow over the symbol. So I hope you're taking notes and making pictures, because when you do these problems in the log kappa assignment or on the exam, you'll have to make sure that you recognize that these are vectors. Now we have to add these two vectors. So we have this vector F1, and we have this vector F2, and we have to add those two vectors. How do you add vectors? Well, we say start with F1, then add F2, oops, the sum of the two vectors is this vector. This is the sum of the vectors. So here's F1. Here's F2. And here's the sum of the two vectors. We can't add the magnitudes. We have to add the vectors. What's F1? KQQ over 9, because the distance is 3. Distance squared is 9. In the direction I hat. I hat is the unit vector in the direction of the x-axis. That's a unit vector, so I put a hat over it. What's F2? Here's F2. Just think of the force of interaction of these two charges. It's KQQ over 9. J hat points in the j direction. So j hat is in the y direction. So here's F1, here's F2. Or I could use this other notation for vectors. I could write down the x component of the vector, coefficient of I hat, KQQ over 3m squared. And here I would have the y component of the vector, KQQ over 3m squared. Now we want to calculate the force. This will be the force if I draw a little parallelogram here. This will be the force that I'm looking for. That's F1 plus F2. So its direction is at a 45-degree angle. Its direction is at a 45-degree angle. So that gives me the direction. Here's X. Here's Y. It has equal components X and Y. So it's at a 45-degree angle in the XY plane. How about the magnitude? Well, I have to calculate the magnitude I could say the magnitude of F1 plus F2 is the square root of F1 plus F2 squared. Using a little bit of high school algebra, that's F1 squared plus F2 squared plus 2 times F1 times F2. When I say F1 times F2 for vectors, I mean the dot product, F1 dot F2. So I could say this is the square root of F1 squared plus F2 squared plus 2 F1 dot F2. But F1 and F2 are perpendicular. So F1 dot F2 is in fact 0. So it's really just the square root of F1 squared plus F2 squared, which again you can see a little easier by just looking at this picture. I mean, look at this little right triangle, or this picture. Look at this little right triangle. This adjacent side has length F1. This adjacent side has length F2. The hypotenuse is the square root of F1 squared plus F2 squared. So I'll have KQQ over 9 squared plus the same thing times 2. Then I take the square root. So that'll be KQQ over 3m squared times the square root of 2. We've often assigned a problem like this on the exam, and it's usually the hardest problem on the exam. In other words, in terms of the number of correct solutions, this is a problem that if we put it on the exam, the largest number of students will get it wrong, because they'll try to add KQQ over 3m squared plus KQQ over 3m squared. That'll be 2 times KQQ over 3m squared. Wrong. It's the square root of 2 times KQQ over 3m squared. This was a video for Chapter 15, Part 1. So far we haven't mentioned the electric field. Part 2 describes the electric field. So watch video for Chapter 15, Part 2, and then read the chapter.